Hi and welcome to this walkthrough of inheritance questions from section 2 of BMAT papers. These are real examples of the BMAT paper questions. They have the date at the top. Make sure you've gone through some of the question tutorials and the theory tutorials as well before you have a go at these style of questions. So in the first question we're looking at here from the 2016 paper, all 4 of these statements are correct. We're talking about a mutation here. Remember, a mutation changes the base sequence, which in turn can change your amino acid that matches with that base, which in turn will change the primary sequence of a protein and thus how that protein functions. You can get a protein that works more efficiently. You could get a protein that works less efficiently. Absolutely. Okay, it's going to affect that enzyme, but an enzyme is a protein. So statements 1 and 2, from what we've just talked about, definitely could happen. Statement 3, a new allele was formed coding for a non-functional. Again, we're talking about proteins that have no effect on the cell. And then we could have something that has a negative effect. Okay, so remember that a mutation can occur due to substitution, deletion, or addition of those bases. And that can lead to a non-functioning or a functioning or a dangerous protein being made. Therefore, our answer is G. So this question asks us for the maximum possible number. That's really important when we continue working this question out. So to get the largest number of our heterozygous mice, we can assume that all dominant mice are heterozygous dominant. So for example, C and little c, and not homozygous dominant, so not big C, big C. All of the recessive mice are homozygous recessive, of course. So they'd be lowercase c. We've got 12 grey mice and 4 white mice. So it's sensible to say that our white mice are the homozygous recessive. We want to maximise our heterozygous, hence the maximum number we can get are 12 heterozygous mice. In this 2015 question, I'm going to label some alleles very, very clearly on my diagram. So the diagram shows results of a breeding experiment. We've got a homozygous black mouse, and I can see that that must be dominant because I've ended up with 4 black mice coming out of that experiment. So if we're going to then presume that my white mouse is going to be recessive in that particular case, and so my black mouse 2 here is going to therefore be heterozygous. Because I can show it in my Punnett square, so my black mouse breeds with my white mouse, and all 4 of my offspring are going to be heterozygous. Okay, so I can say that my second mouse over here is going to be that genotype. Then, my second thing I need to consider, mouse 2 is then allowed to mate. Mouse 1 was then allowed to mate with mouse 2, and it says using C, but I've started using B, but I can just change it afterwards anyway. Let's keep it as B for now. So we're then going to mate mouse 2 and mouse 1. Let's do another Punnett square. So uppercase B, lowercase b, and we're going to breed those, and we're going to get 2 homozygous dominant and 2 heterozygous as well. So we're being asked details of the offspring where mouse 1 and 2 are mated. The percentage of heterozygous, well, I can see here that I've ended up with 50% heterozygous. So I'm going to get rid of any option that suggests any other percentage. Then we're looking at our phenotype. We are going to have all black mice in this particular case. And immediately that gets rid of option E and option F. So I know my answer is D, but let's have a look at our final. What's our genotype? We've got both homozygous and heterozygous. I can see them here. Okay, so my answer is D. So in this question from the 2015 paper, there's a little bit of a trick, a sneaky part that's got in there that you need to be careful to avoid. So it tells us that the Y chromosome contains the genes necessary for making sperm. Now, we have been told what the ratios are to get male and to get female. Whether there's a Y chromosome or not there is not relevant. It's whether it gets turned off or on, and that's dictated by this information here. So we can just ignore the Y chromosomes. because the gene for sperm production can be activated or dormant depending on the X to A ratio. So it has no effects on sex determination. Let's have a look then for these ratios. So for XAA, this one at the top, we can see that we've got a 0.5 to a 1 ratio. So therefore, this is going to be male. It tells me up here. So I'm going to get rid of anything that suggests that it might be female. Then I'm looking at my next column. Again, I can see I've got an X to 2 A's. So again, I have got a male. So let's get rid of F and E. On to our next. We've got a 1-to-1 ratio. Okay, so we know it's going to be female. Our only two options left are female. And again, I've got a 1-to-1 ratio. Both my options left are female, and I agree. And finally, I've got a 1-to-1 ratio because I am just ignoring these Y chromosomes. So with a 1-to-1 ratio, they're going to be female. So my answer is G. So a question from the 2014 paper. This woman has a recessive genetic condition, but neither of her parents have the condition. So it suggests that they have to be carriers. If we look at statement 1, both her parents are heterozygous for this gene. Well, she must have received one recessive allele from one parent and one from the other. So they both must have been heterozygous because they don't have the condition, but they must have had a recessive gene for this to pass down. So that statement is correct. So our second statement, one maternal grandparent and one paternal grandparent have the condition. Now this, remember the statement says, which could not be true. This statement could be true, absolutely, because they could have then bred with someone else and they would have brought that recessive gene into that family line and passed it down. So that statement could definitely be true. Statement C, one maternal grandparent and one paternal grandparent are heterozygous for this gene. Well, for the same reasons, yes, that could be true. If they have the condition, then they would be heterozygous for that particular gene. Statement D, all her grandparents were carriers of the recessive allele. Again, that could absolutely be the case. They could be recessive, they could be carriers of the recessive allele, breeding, passing that on, and their children may not have the condition, but they could also be carriers. So we're just thinking about the fact that that recessive gene could still be being carried down. So that could be true. And finally, both parents are homozygous and the mutation occurred in the DNA of a gamete from one of her parents. So no, this statement could not be true. We'd have to have one recessive allele from one parent and one from the other to make the person homozygous recessive. We could not have a mutation in just one gamete. Okay, so this statement could not be true. So our answer is E. So in this 2013 paper, let's define the dominant allele as T and the recessive allele as lowercase t. So we're going to cross a Manx cat with a tail. So Manx cats with two recessive alleles have a tail. So two recessive alleles, my Punnett square. And I'm going to cross it with a Manx cat without a tail. And here it says that heterozygous lack a tail. So I'm going to have my heterozygous and I'm going to draw my Punnett square. So capital T, lowercase t, and as such. There we go. So I can see here that none of them have passed away. And I've got two. I've been asked what percentage of Manx cats without tails. So how many are heterozygous? I can see 50% are so far. So I'm going to eliminate anything here that has any other number other than 50%. And then I'm going to do my second statement. So a Manx cat without a tail. So we've got, again, heterozygous, crossed with a Manx cat without a tail. So let's have a look and do our cross. So we've got a homozygous dominant there, and then we've got... So I can see I've got two heterozygous. So I've got two cats without tails there. But there's something that you need to be really careful of here. I've got a dominant disordered cat. So I've got individuals with both dominant alleles die before birth. So when something passes away, it's no longer part of the population. And we've been asked what shows the percentage of cats in a population of the two crosses. So now I need to work out what these two are as a percentage of the total. So for every 3 of my cats, 2 that live, that are in my population, 2 are going to be without a tail. Therefore, that percentage is 67%. So it's a little bit of a trick there. My answer is C, 50% and 67%. Okay, so in this question from the 2012 paper, statement 1 is too vague. So it doesn't tell us whether that offspring dies in the womb or after birth. And if it died in the womb, we wouldn't be able to process the alleles to check in that particular case. So it is just too vague. We cannot say that statement's true. And then we've got only a small number of offspring being produced. So a ratio of 3 to 0 could happen if only a small number of offspring are produced. So for example, we could have 3 offspring with all 3 of the phenotypes. So that statement could be true. Remember, read the question carefully. It's asking what could be true. And then our final statement of chance. So as the ratios can be amplified, i.e. 3 to 1 is the same as 6 to 2, it may be due to a matter of chance that the population of offspring repeatedly express one phenotype. So fertilization is a random process, hence the outcome is only probabilistic, okay? So we can see here that that could be down to chance as well. 2 and 3 could be, so the answer is D. So I'm going to be annotating in this question from 2012. What is the minimum number of people shown in the family pedigree who must be heterozygous for the 2 situations described in the table? So only U shows a recessive condition. So let me create a letter. So D, lowercase d, only U shows a recessive condition. So for you to have obtained 2 recessive alleles, it must have picked them up from its parents. And its parents cannot have the disorder because we've just said only U has it. So they both need to be heterozygous. Okay, and then we need to think in terms of S. How is S going to pick up that allele? Because it's still got it. It still has this recessive allele in order to pass it down. We're looking for the minimum number, the absolute minimum number. So what could P and Q be such that the smallest percentage would give us a recessive allele? Well, P and Q could be dominant and Q could be heterozygous. And that would give us a really small, or the smallest proportion possible where it doesn't have the condition, but it's still able to pass that recessive allele down with 50%. So therefore, one of these, let's say Q, could be heterozygous recessive. So in that particular case, we've got 1, 2, 3. That's the minimum for U. So let's get rid of anything that doesn't have 3 as an option. Now, we're going to change what's happening a little bit. We're going to realise that we've been told that now only R and U have the condition. So let's add in R. It's got to be a homozygous recessive. Therefore, it's got to have picked up a recessive allele from both P and D, of course, for the same reasons as we were talking about with U. Okay, in order to be homozygous recessive, and the parents will not be affected, and they will both have uppercase and lowercase. Therefore, we can see the minimum here is 1, 2, 3, 4. So my answer is E. So in this question from the 2011 paper, it tells me that the condition of the shaded is caused by the presence of at least one allele. Therefore, statement 1, the condition is dominant. I know that's true because when a condition is dominant, I only need one allele in order to have the condition. Statement 2, the sperm from T carried the allele for the condition. So as the condition is dominant, it could be that the sperm from T has carried the allele, and therefore due to random fertilization, that has then been passed on to U. So, which of the following are possible reasons? Yes, that could be a possible reason. And then finally, 3, a mutation present in an egg of S. So statement 2, or statement 3, does not contradict with statement 2. Okay, so it suggests that the female egg, a mutation can cause a change in the base sequence, of course, resulting in changes within one of those alleles. So the previously non-functional allele may now code for the condition after the mutation. So that could have happened. So we can see that all 3 of these is a possibility. So the answer is D. So in this question from the 2010 paper, I'm going to annotate my tree diagram very, very carefully, or my genetic cross. So it shows that P and Q are carriers of a recessive allele. So I'll give them uppercase G and a lowercase g. And then I'm going to add on R and X. So only individuals R and X have the condition. So they're going to be recessive. Now, immediately that gives me some information. I know that if X is recessive, then U and V don't have the conditions. They both must have been carriers in order to pass that down. What I can also say is, so U has got a 100% chance of being a carrier. So I'm going to eliminate anything here that suggests that U isn't a 100% chance. You can see those were all 50. So now we know that R is lowercase g. In order for W to be unaffected, S has to be either heterozygous or homozygous dominant. It cannot be affected by the condition. So let's do this cross here quickly. So we'd have R's, both lowercase g's, and then we'd have S, let's try it as heterozygous. And then let's try it as though it was homozygous dominant. So both of these options give me situations where W is unaffected. Therefore, I can confirm that S is 50% likely, in this particular case, to be a carrier. If I just jump back to the start a minute and just quickly cross P and Q, I can get some really useful ratios that we're searching for. So if I cross P and Q, I've got a homozygous dominant, I've got the option of 2 heterozygous, and I've got the option of one of our offspring being affected. So I can say that my ratio is 1 GG, 2 heterozygous, and 1 homozygous recessive. So we have found one of our guarantees. So U is definitely going to be one of my bigger case and lower case. We've got S, which has got the option of either being one of these or one of these. So it's reasonable. We know T doesn't have the condition. So it's reasonable. We've got a 50% chance as well of T being a carrier. So my answer is E. Okay, so this question from the 2009 paper, it tells me that individual A is homozygous dominant. So I'll give it capital P, and B is homozygous recessive, so lowercase p. It's a little bit hard to show them the difference between those. What is the percentage probability of individual F being homozygous recessive? So homozygous recessive, so lowercase p, if E is homozygous recessive. Let's do that first. So if we've got homozygous recessive. So let's cross A and B first. So we've got 2 uppercase P's, 2 lowercase p's. So all 100% of my offspring, so D, is guaranteed to be heterozygous. Okay, so that helps here. So let's cross D and E now. So we've got our heterozygous, and then E, we've been told in this question here, they want us to try it out as if it's homozygous. So lowercase recessive. So capital P lowercase, capital P lowercase. So I can see that the percentage probability that the individual F is homozygous recessive is 50% in that particular case. And let's do our second option. So let me eliminate quickly. So I can just eliminate anything that suggests anything other. So we've got our 2 50% left. And then the E is heterozygous. So let's do our D again. So we know that D has to be heterozygous, but now we're crossing it with another heterozygous. So uppercase, lowercase, lowercase. Okay, and again, so I've been asked what is it that we've got? F is homozygous recessive. I've only got one here that is homozygous recessive, so that is 25%. Therefore, my answer is C. So in this question, I'm going to go statement by statement. So statement A, I can see that it's correct. Okay, this is a correct statement because the risk increases by 0.5. So I can see in there it goes from 1.0 to 1.5 and from 4 to 4.5 in both types of alcohol intake. Statement B is also correct because I can see that there's a positive correlation. So a positive correlation between the increase of the variables. So the number of mutant alleles present and the risk value. As the number of mutant alleles present increases, so does the risk value. So that is a positive correlation. Statement C is also correct because alcohol intake significantly increases the risk, from being in the range of 1 to 1.8 to in the range of like 4 to 6. That is greater than a 4-fold increase, so it is significant. So statement E is also correct, as the difference between the risk values with 1 and 2 alleles for heavy drinkers is 1.5. So we did 6 minus 4.5 is 1.5, and it's only 0.3, so 1.8 minus 1.5 for light drinkers. So that's definitely correct as well. And statement D, that is our incorrect statement. The presence of at least one mutant allele is the main factor for increasing risk. So this is because it directly contradicts statement C, which tells us that it's heavy drinking. Heavy drinking is that proven main factor which increases the risk. Okay, so our answer is D.